Yes, so there's another method for solving systems of linear equations, which we have not looked at. I'm aware of that. It's called graphical methods. And they will combine that with the graphs of the functions that we're going to learn today in the next class. So today I want us to have a brief review of functions. And then we will look at three main functions. So we have rational function, we have exponential functions, and logarithmic functions. These are very common functions. They have numerous real-life applications. You can use them to study population dynamics, to study spread of disease in a country or in a region. You can use them to understand return on investment. For example, when you invest your money in the bank, it is some of these functions used to calculate how much interest your money earns and how much are you supposed to get at the end of the interest period. So first of all, I would like to define a function. We defined a function before, just a review. So definition, let A and B be sets. By now you're all familiar with sets, a collection of elements. Then a function denoted by f of the set A to the set B is simply a rule that assigns to each element of A a unique element in B. So we're looking for a correspondence. So each and every element in the first set is exactly one element in the second set. So if this is your set A, this is your set B, then for your rule to qualify to the function, every element of A must be associated with only one element in the set B. We want to avoid situations where one element from A is associated to two elements in B. So the examples of functions that we're going to look at today are rational, exponential, and logarithmic functions. So firstly, rational functions. Rational functions. We have done polynomials. So a rational function is a quotient of two polynomials. A quotient of two polynomials. And you're aware that a polynomial in a variable x is simply an expression of the form a0 plus a1x all the way to an x to the n. This is of degree. So n must be a natural number. This is what we call a polynomial in the variable x. It's of degree n, where n is the highest exponent. So taking a quotient of any expressions, any such expressions gives you a rational function. For example, let's say you have 2x plus 1 divided by 4x plus 5. This is a rational function. The numerator is a polynomial, the denominator is also a polynomial. So this is a rational function. Another example, you can take maybe 2x cubed plus 4x plus 6 divided by x power 10 plus x. That is also another rational function. You can see the numerator is a polynomial. The denominator is also a polynomial. They're both polynomials in x. So this is a rational function. Any question on rational functions? Any question on rational functions? Just take two polynomials and divide them, then you get a rational function. Question on rational functions? We will see how to graph such functions and see how you can deduce information from them. This rational functions are applied especially in the theory of electricity. To understand how current flows, we need an idea of rational functions. Any question on rational functions? Cool. The second type of function is called exponential functions. Exponential function. Exponential function. So definition, again, this is just a repetition. We saw some of these definitions when we were looking at exponents, integer exponents. So the definition, an exponential function, with the base a and exponent a variable x is an expression of the form. So we have to call it f of x to be a raised to x, such that a is in the interval from 0 to infinity, and a must not be equal to 1. So remember here, it is the exponent that is a variable. So it is x that is changing. The base is constant. When I say a is in the interval from 0 to infinity, I'm only interested in positive real numbers, okay? And I don't want the base to be 1, because 1 raised to anything is always 1. So when I take 1 raised to 2 or 1 raised to 4 or 1 raised to anything, it always give you 1. So that's why we do not want a base 1 for exponential functions. Any other positive real number can be used as a base for exponential function. Let me give you examples of exponential functions. So for example, let's say you have a function with a base 2 and a variable x. So in this case, a is 2, x is our variable. Let us see some few evaluations of this function. So suppose x is 2, then f of 2 will be 2 raised to 2, which gives you 4. How about if x is maybe 4? So then you compute f of 4, it should give you 2 to the 4. So I replace x with 4. This gives me 16. What if I pick x to be 10? So f of 10 is simply 2 raised to 10. Lastly, 30, f of 30 will be 2 raised to 30. Those who have calculators, please compute this and give me these values. What is 2 raised to power 10 and 2 raised to power 30?
1024.
There's an observation I'd like us to make that. So this is 1024. How about this?
And 73, 74, 18, 24.
73.
74, 18, 24.
So this is, it's a very big number. Suppose you have another function, which is not an exponential function. Let's say I take a function like x squared. X squared is not an exponential function. This is a power function, because the variable is the base. So this is a power function, not an exponential function. Then I want to compute the same values and we compare. So let's see g of 2. G of 2, so x is 2, that will be 2 squared, get a 4. How about g of 4? G of 4 should be 4 squared, that gives you 16, okay? Well, how about g of 10? G of 10, that should be 10 squared, which gives you 100. Lastly, g of 30, that should be 30 squared, which gives you 900. What can you say about the values of the function g and the values of the function f? Can you give a comparison? The values of these functions. Remember, I'm taking the same arguments, 2, 4, 10, and 30. for both functions. Could you give a brief comparison for the values of the functions? Anyone? Compare these two values. What can you observe from the values of the function g and the values of the function f? We have done evaluation at the same arguments, 2, 4, 10, and 30. 2, 4, 10, and 30. What can you say about the outputs that we have? Hello? Are we there?
Can you repeat the question, please?
I want someone to compare the values of the function f and the function g at the points 2, 4, 10, and 30. We have evaluated the functions f and g at 2, 4, 10, and 30. Can someone give me a comparison of the values? The values of the function I'm referring to are this 4, 16, 10, 24, that number, 900, 100, 16. Compare those values. What can you say about them?
So for the function g, I think for starting on the 10th value, so the base is the exponent and the exponent was the base. So it just interchanged.
I don't know whether my question is not, maybe my question is not.
They are all square roots.
They are all?
Square roots.
They are all square roots. Hello, come up again. Okay, 4, 4, and 16, that's okay. What can you say about 10, 24, and 100? And 900 and this big number? Okay, so you realize that when dealing with exponential functions, any slight change in the argument leads to a very big change in the output. So for example, when we change from x is 4 to x is 10, we move from 16 to 1024. That's a difference of 1008, okay? And then when we move from 10 to 30, just a difference of 20 gives you this big difference. It's in millions because this it's actually a difference in millions, just a difference of 20. But other functions, for example, a power function, a small change in the argument still gives you a corresponding small change in the output. But with this, you might want to call it dramatic or whatever, such a big increase. These exponential functions are still very useful, for example, in modeling the growth of population in a country or the spread of disease during a pandemic. So the observation I wanted you to make is that a small change in an exponential function leads to a big change in the output. So the exponential function is when the argument is the exponent, or the variable is the exponent. I would like us to see some special exponential function. So we will define a number e as, so the limit as n goes to infinity of 1 plus 1 over n raised to n. We made this number, it's an irrational number.
Do you mind writing in bigger, like bigger handwriting? Yes, thank you.
So let's define a base e. This is the usual Euler number as the limit as n goes to infinity of 1 plus 1 over n raised to n. Is that better?
Yes, thank you.
Is that clear? So this
Thank you.
Euler number that we have seen before. And it's approximately 2.71828828459045235336. It goes on and on forever. But these are the first 20 values for the number E. You can verify this from your calculator. Just pick any big number. For example, 10 million. Pick any big number, let's say 10 million. And try to compute 1 plus 1 divided by 10 million. All of this raised to 10 million. You will see that this number becomes closer and closer to this as you increase this value to maybe a billion, a trillion, or whatever. So this is a very important number. We normally call it the natural base for logarithms. So a definition, natural exponential function. Natural exponential function. Say that when the Euler number is used as the base, we get the natural exponential function. Exponential function. So the function is h of x is defined as e to the x. E to the x, where e is the Euler number. Euler's number. It's this irrational number. E is irrational, so there's no exact representation for e. We can only approximate it to some decimal places or as much as we want, but there's no exact word, just like pi, it's an irrational number. So when you use this Euler number as the base for your exponential function, then you get the natural exponential function. Some books just call it the exponential function. Let's see an application of this exponential function in population modeling. Is there any question before I give you an example of an application of this function?
So I have a question.
Yes, go ahead.
So can you repeat the definition of E?
The definition of E.
Yeah.
You remember when we introduced the real numbers, the irrational numbers and rationals, and we gave some few examples of irrational numbers?
Yes, yes.
So remember the number E. We talked of E and pi.
Yeah, they were irrational numbers.
Yes, they are irrational numbers. And the definition of E is that you take the limit of this expression, 1 plus the inverse of n raised to n, as n becomes bigger. So when I say n goes to infinity, I'm simply referring to n becoming bigger and bigger. For example, let us do some simple activity here. Okay, I hope you guys have calculators. N, and we want to compute 1 plus 1 over n raised to n. Let's see what we get. So let's start maybe with 1,000. Then we go to 10,000. Then we will do 10 million. Okay. So here, compute for me 1 plus 1 divided by 1,000. All of this raised to 1,000. Just put this in your calculator. Someone else to compute 1 plus 1 divided by 10,000. All of this raised to 10,000. And then lastly, we'll have 1 plus 1 divided by 10 million. All of that raised to 10 million. Put this in your calculator. So what do you get for 1,000?
2.716923932. 2.716923932.
Okay, let's stop at 2.7169. How about 10,000?
5.
10,000? Just put in your calculator and read for me what you get. You can even use the online calculator.
2.718146.
71814. Okay, how about 10 million?
2.71828.
2.7828. Did I get that?
Yes.
Cool. So you can see the first 5 digits agree with that of our definition. Okay, and so as you increase the value of n, you'll be approaching this value of p. So you can use bigger numbers like 10 billion, 10 trillion, zillions, quintillions. If you use those big numbers, so as this n becomes bigger and bigger, as it goes towards infinity, the number that this limit will approach is the definition of E. E is simply the Euler number, and these are the first 20 digits of the Euler number. You don't have to remember this, okay? Just have an idea of the definition. This limiting value of the expression 1 plus inverse of n raised to the n. You don't really need to cram this because this is in your calculator. In your calculator, there's a button with the symbol E. That button will always give you the Euler number when you ask and when you need it. Although in the calculator, it's only up to, I think up to 4.5. The calculator only has up to 4.5, but a computer can give you a larger value. Abdi Hakim, did I succeed in answering your question?
Yes, sir.
This is how we obtain E. So if you want to obtain a better approximation, just increase the value of this number. Try a billion, try 10 billion, 100 billion, 100 trillions, zillions as you proceed. So shall I give an example of an application of this exponential function?
Yes, sir.
Cool. So with our definition of exponential function, when we are using E as the base, then we get a natural exponential function. It's a very popular function, especially those of you who study engineering or study differential equations or partial differential equations. Let's look at an example. I'll give you 2 examples. One example is in population. So this is a population modeling. A disease outbreak in an area has been modeled by the following function. So P of t is 10,000 divided by 1 plus 999 exponent negative 0.5 t. So P of t is the number of infected persons. Let's say infected people after T days So you see the exponential function. This is the E that we've just defined. It's an exponential function, 0.5t. T is the number of days. And this expression gives you the number of people infected by this particular disease after T days. Then you need to answer the following questions. So
What's the number after the E?
negative 0.5t.
Okay.
Yeah, this is negative 0.5t. This is negative 0.5t. How many people are infected initially? How many people are infected initially? So we bracket at time t0. And then 2, find the number of infected people. Find the number of infected people. After 2 days, 3 days, 100 days. Lastly, theta days. So we have been told that a disease outbreak in an area is being modeled by this function, P of t. So this is the population that is infected by a disease after t days. It's given by 10,000 divided by 1 plus this exponential function. And this is the number of people infected after t days. So first question, how many people are infected initially? So how many people have the disease initially when you start counting? Or when the outbreak has been declared, that's at the time t0. Then find the number of infected people after 2 days, 3 days, 100 days, and then theta days. Any question on the question before we show how to go about this? Is there any question about the question? You guys are so dull today. People are not talking. Any question? Anything that is not clear about the question?
Excuse me, sir.
Yes.
Over there, the function, it's P what?
It is P of,
Like, can you read?
this is P of t.
P of t is equals to 10,000 over
1 plus 999 times the exponent of negative 0.5t.
Okay, thank you.
Okay, so I'm going to write the solutions here. So the first question is, how many people are infected initially? You've been asked at time 0. So before you start, so at the beginning, how many people are infected? You simply need to compute P of 0. So initially, that means at time t0, compute P of 0, just replace t with 0. So that should be 10,000 divided by 1 plus 999 exponent negative 0.5 times 0. So this gives us 10,000 divided by 1 plus 999. So what is exponent of negative 0.5 times 0?
0.
1.
We have two answers, 0 and 1. Is there any other different answer? The person who said 0, why do you think it is 0? Or the person who said 1, are you able to defend your answer? Hello?
I think, sir,
Yes.
the number raised to 0 is 1.
So any number raised to 0 is 1. Yeah, so the person who said 1 is right because this is exponent 0.5 times 0. 0.5 times 0 is 0. So in other words, you have exponent of 0. So exponent of 0 is 1. So here we will have 999 times 1. Fine. So this gives you 10,000.
What about the E?
The E.
Yeah.
Remember this law of indices, a raised to 0 is 1. Where is any number? Hello?
But it's not 0, it's 0.5.
Yes, it is 0.5. So you have here exponent of minus 0.5 times 0. What is minus 0.5 times 0?
Oh yeah, 0.
Yeah, so this should be the same as exponent 0. Notice exponent 0. You can even do this in your calculator. We know any number raised to 0 will always give you 1. Anyone having a question about this? Anyone who does not believe this? Anyone who does not trust this? So we gave the laws of indices. They still apply here because these are the exponential function. So just that the exponents are variable now. So any number raised to 0 will always give you 1. So in this case also you have exponent. So when you multiply the powers, you get a 0. So exponent of 0 is 1. So that's why I have 999 times 1. Now at the denominator you have 1 plus 999, which is 1000. So what do you get? When you divide that,
10.
you divide that, you get 10. So initially, only 10 people are infected by this disease in that particular area. So initially, at the time 0, we've just substituted P for 0. Any question on this? So the number of infected people after 2 days. I'm going to draw a table because the procedure is the same. So we have T and then P of T. So we had 2 days. There was 100 days, and then there was theta days. Is there any that I've missed?
Those 3 days.
There was also 3 days. Okay. And you know what the function is. So at 2, simply replace T with 2. So you will have 10,000 divided by 1 plus 999 exponent negative 0.5 times 2. Replace T with 2. Same for 3. You'll have 10,000 divided by 1 plus 999 exponent negative 0.5 times 3. Same for 100. 10,000 divided by 1 plus 99 exponent negative 0.5 times 100. Same for theta. Theta is any number. So that should be 10,000 divided by 1 plus 999 exponent minus 0.5 times theta. This one is just going to be 10,000 by 1 plus 99. You cannot simplify it any further. Minus 0.5 theta. But the first 3, we can at least give approximations. What do you get when you use the calculator for the number of people infected after 2 days? Someone work out this.
About 27.
What do you get exactly?
27.21.
27. Yeah, so that's approximately 27. Huh? How about 3? Someone to do for 100. Please, let's save on time. Just put this in the calculator, the way it is. 10,000 divided by that. I'm going to use brackets. Or maybe this is too simple. I should leave it for you guys. Huh? Once you've done this, it's just the work of the calculator. You just put this in the calculator. Anyone who has a problem with this?
Yeah. I didn't get 27 for the first number.
You didn't get 27?
Yeah.
What did you get?
39.8.
39.8. Confirm that. The person who gave 29. So let me do this just a minute. Is there any other question? You do the same for 3 and 100. Okay.
For 3, I've gotten 44.66.
44. So that's approximately 45. Huh? Do the same thing for 100. Just put this.
And for 100, it's 10,000.
10,000.
Yeah. Somebody else can confirm because I'm not sure about that, but I've gotten 10,000.
I've also gotten the same.
You also got 10,000.
Yes.
Okay. Yeah. So any question on this? So this is very simple. We're just substituting. Whether it's t, put 2. Whether it's t, put 3.
Excuse me, sir, I have a question.
Whether it's t, put theta. Yes.
For the last one, the theta, what is the answer? It's 10,000 over?
This one here is 10,000 divided by 1 plus 999 exponent negative 0.5 theta. So in the formula, where there is t, just put theta there, and that's the answer. You don't know what theta is. Theta is any number.
Okay.
Yes. Shall we go ahead?
Could you do the first number? Because I'm still getting the same answer.
You're still getting the same answer when t is 2. Hello?
Yeah.
You're getting the same number when t is 2.
The E in the equation.
Which e?
No, I'm talking to that one who is getting the same answer. It's because she had not put the, 1 plus 999E. Maybe she's probably putting it directly without that E, the Euler.
Okay, are you seeing my screen? Are you able to see my calculator?
Yes.
Yes.
Calculator. So let us see. First bracket. Then we do 1. No, it's 10,000. Huh? 10,000 divided by. That's not happening. Right. Stop. So bracket. That's not happening. Okay, cancel that. 10,000 divided by bracket. I wasn't opening this calculator. Oh, it's not happening. Oh, okay. Now see the problem. So let's do this 10,000 divided by, so bracket, I want to put 1 plus 999. Are we there? Exponent. I have to go back here. 1 plus 999 times times the exponent is the power. Okay, exponent is here. Exponent in bracket negative 0.5, 0.5 times 2. Then I close the first bracket, close the second bracket, and see what we have. Very good. Oh, good. This calculator is very hard to use. Let me use the online one.
So even the calculator I'm using, I have not got any right answer at all from the beginning.
You didn't get any right answer.
None at all.
I'm using, so the online one is here. It's you just put 10,000 divided by 1 plus 999, then exponent of, so we want negative 0.5 times 2. And we get that. So if I want 3, I'll just put 10,000 divided by 1 plus 999 times exponent.
Excuse me, sir. Are you sharing your screen?
Oh. Yes, this is my screen. Exponent. So this is exponent of minus 0.5 times 3. Close the bracket, close the bracket. 44.6, which gives you approximately 45, okay? When you want for 100, just put 10,000. So the brackets are very important. Divide by 1 plus 999 exponent. So exponent of bracket negative 0.5 times 100. So 100. Close the bracket, close the bracket. That gives you 10,000.
How do you write the exponent on the calc?
In the calculator, just take this symbol. You see this symbol E.
You can just use alpha E.
Alpha ln.
Oh, those who have the calculator. For those of you who have the scientific calculator, I could show you, I can show you how to use that maybe after class. I can show you how to use it. The one I have on this computer is very hard to use. If you are using FX82 or FX991.
So how do you negative 0.5 multiplied to 100? Just
put negative 0.5 times 100. You have to put it in bracket. Exponent and then in bracket negative 0.5 times 100. I see my mouse. Try to.
I guess he's asking on a calculator.
On a calculator? Yeah, on a calculator. So you will do this exponent. How? Which calculator are you using? This one I have on my computer is very hard to use. I've never used it. Do you have a scientific calculator? Jed? Hello?
yes, I do. Yes, I do.
I can show you how to use that one after class, please. I can show you how to use that after class.
No.
Okay, I can try and explain to him like the raising power part, but we have the root of x with an arrow pointing upwards, like an inverted V.
Yeah.
Yeah, you use that one to mean that it is to the power of
Oh, when raising
and
the
then you
power.
Yes.
Okay, that's fine, but it's just the answers I've been getting. Then it's okay.
No, no,
Let's
just
continue.
like I can show you. This is something very easy. I can show it to you. It's very easy. You'll just show me. You just share your calculator. Then I'll show you the buttons to press. Okay.
Okay.
I don't know whether I can find the. Let me see. FX. 99. Even this one will go 991 E plus.
Mine is the FX82 MS.
2 MS. 2 MS. It's just giving me the. Let me see if this can. Go. I'm trying to magnify. It's not magnifying, so I can show you this after class, please.
Okay.
I'll show you this. It's very easy. So if you're asked to compute the number after some days, just replace the number with the variable that is given. One last example on use of exponential functions. So second example, finance, in simple terms. So when you invest some money and you want to get interest, so you normally have, let's say, the principal. This is the amount invested. Okay. Then A will stand for the amount at the end of the investment period. And of course, I is the interest in percentage, interest per period. Okay, normally given in percentage, could be 10%, 1%, 2%, 3%, depending. So let's say you invest.
The light is making the board blurry.
How about there?
You've gone far.
It's gone far.
Yeah.
But is it visible?
Again?
Is it visible?
Yeah, that's better. Thank
You can use that. Huh?
Yes, thank you.
Yeah, so suppose you're investing some amount P, and then the interest you earn is P times I, P times the percentage. So at the end of the first period, what you will have will be P plus PI, which you can factor P out and write this as P into 1 plus I. So we are investing the amount P. This is the amount invested. Then the interest will be the interest rate I times P. So our money has earned the interest PI at the end of the first period. So the total amount we have is the amount you invested plus the interest, which is P plus PI. You can factor out P and get P into 1 plus I. Okay. You can show that. So this is after the first period. This is after the first period. The first period. You can show that after K periods, we will have the amount as P into 1 plus I raised to K. And the expression 1 plus I raised to K is common expression. It's simply an exponential function with the base 1 plus I. Okay, this is an exponential function. So we can actually use this to calculate the interest rate, to calculate the interest or the interest rate or the amount of the principal, any of these variables. Now, suppose that you divide the interest period. Let's say you're doing it in years. So let's say we divide the interest periods. And periods. Interest period n periods. Then amount given by A is P into 1 plus R divided by N raised to NT, where I is simply R divided by N. So if it was an interest rate of, let's say, 10% per annum, and you want to compound your interest at the let's say, per month or per 6 months or per every 4 months or per day, then this is the number of periods. So the total will be A P into 1 plus R over N raised to T. So in this expression, P is the principal, bracket amount invested.
Where's the R and the N coming from?
N is I'll explain that shortly. N is the number of compounding periods. R is the interest rate per annum. T is the time in years. So you ask, where is the R and N coming from? I started by saying I is the interest rate per annum. It's normally given in percentage, okay? So let me give you an example. For example, let's say I invest 10 shillings at a rate of 2% per annum, 2% per year, okay? And I want the interest maybe after 4 years time. So I is simply 2%. If I want to find the amount of earned by this compound interest, so compound interest simply means after every interest, you add the interest to the amount, and when calculating the next interest, you consider the amount as the initial principal plus the interest. It's different from simple interest, which just calculates the whole sum interest and then adds it to the principal. So for example, in this case, after 4 years, I'm expecting 10 shillings plus 1 times 2 divided by 100 raised to 4. This is just the simple compound interest. But suppose I wanted that after every 3 months, I put the interest on top of the principal and proceed. After every 3 months. 3 months will be too big. Let me take 2 years. Because 3 months will give me 6 periods. So the first 3 months, now suppose you compound after every 3 months, every 3 months. So first of all, compute the interest for the first 3 months. Now let's see, the amount for the first 3 months should be 10 multiplied by 1 plus. So this is 2% per annum. And here you're dealing with months. So it means per month it will be, so per month should be 2 divided by 12%. The reason for that is 1 year has 12 months. So if in 1 year you earn 2%, in 1 month, you should add 12 divided by 12. 12 is the number of months in a year. So the interest should be 12. 2 divided by 12%. So if I'm doing for the first 3 months, I should take 2 divided by 12. That is for 1 month, but then I'm dealing with 3 months. So this gives me, just work out what this will give. This is 10 multiplied by 1. What is 2 divided by 12? 2 divided by 12 is 1 over 6. 1 over 6 cubed. What you get when you compute this? Someone put this in the calculator. Hello? Hello?
15.87.
15.87.
This is 15. Point 87. When you're compounding after every 3 months, so the first 3 months, calculate the amount. Then now, the next 3 months, which will be now be investment after 6 months. So let me call this A3 to mean for the first 3 months. Then A6, which will be the amount after now the 6 months, which will be 6 months. I now use this as the principal amount. So after adding the interest to the initial amount that we had, the principal, this is now what we use as the principal. So now when calculating the interest for the next period, you consider this amount as the principal. So you take 15, so 15.87 multiplied by 1 plus 2 divided by 12 cubed. What does this give you? Now I use this 15.87 as the principal to compute the amount for 6 months.
$25.20.
Sorry?
1.
25.20.
5.20. And remember here, we consider the first interest earned in the first period. So we are taking the period in blocks of 3 months. So in the first 3 months, you earn the interest, which is the difference of 10 and 15. So that's 5.87. We have added that interest to the initial amount to get 15.87. Now, this is what we use our principal when calculating interest for the next period. This is how you do compound interest. But suppose I want to find the amount of money after 6 months without going through all this, computation. So what I will do for the person who was asking where R and N are coming from, I can compute this by just taking the amount 10 multiplied by 1 plus, so the interest rate is 2 divided by 12, but I'm considering 3 months, okay? So this times 3, all of this raised to 3 times 2, because I have 2 periods, the first 3 months and the second 3 months, that is 6. What does this give you? Hello?
Mine has 68.
Minus 68.
No, mine has 68.
668.
Yes, but I don't even have decimals. I need to change the settings.
Interest rate is 2% per annum. Divided by 12. Oh, sorry.
13.8.
I'm getting the same 13.8.
13.83.
Just a moment. 2 divided by 12. 3. How about this? 10 times 1 plus 6 divided by 12. Or 6.
For you to get 25.21, you don't multiply with you don't do the 6 over 2, you do the 2 over 12, and then into brackets power of 3 multiplied by 2. That's when you would be able to get the 25.21.
Oh, 3 divided by 2.
Yes, the 1 plus 2 over 12, then into brackets 3 to the power of 3 times 2. That's when you'll be able to get the previous answer, the 25.21 or 25.20. Yeah.
2 divided by 12 raised to 6 now.
Yeah. Yes, like that.
So I have a
Because the
question.
last one gives us 113.91.
This gives you
25.21 or 25.21.
No, let's do okay. 2 divided by 12.
I think it's correct because you're already doing the 2, the 3 to multiplied by the 2. The power 3 multiplied by 2, so it will equal to 2 periods, like to represent the 2 periods, the 3 months, 3 months.
Yeah, I mean, I understand why they took, but
yeah.
But now here, they should also be okay. I now get it. So
yeah,
the initial rate, interest rate was 2% per annum. The interest rate was 2% per annum. Okay.
Yes.
And now we're dealing with an interest rate of 2 divided by 12% a month. So here you actually have 12 periods because in a year there are 12 months. You're compounding per month, okay? So that's why to find the interest amount is 2 divided by 12. 2% is earned per year. A year has 12 months. So in 1 month, you will earn 2 divided by 12. And the reason we are multiplying by 2 is because we have 2 periods. 3 here is the time. So you're calculating the interest after 3 months, but you have 2 chunks of 3 months. The first 3 months, okay, for the first interest, and the second 3 months for the second interest. So it should be 1 plus 12 divided by 12 raised to 6.
Yes.
Which gives 25.21. So when you are asking for R divided by N, I hope with this example I can now explain. Suppose you have invested money over some period of time. Let's say you've invested your money in T years. You invested your money in T years, but then you don't want the compounding to be done after the whole 3 years. If it could be 5 years or 10 years. You want the compounding to be done in sub N periods. You have n periods, n periods. So the first period here is t divided by n. There's another period here, t divided by n. N of them. Then the interest for every period, the interest rate for every period will be the interest rate per annum divided by n, the number of periods. So n, this n is the number of periods. N is number of periods, number of compounding periods. Compounding periods. So if initially you had an interest rate, of R% per annum, then for each and every period, we'll have an interest rate of R divided by N. A period where N is the number of periods. So in this our example, each period is simply 3 months. Each period is 3 months. That's why I have 2 periods. I'm compounding the interest after every 3 months. So the whole investment is in 6 months. That means I will have 2 periods. I will have the first period is in 3 months. The first 3 months, that is the first period. The second period is in the second 3 months, giving you a total of 6 months. And you notice that 3 times 2 will give you 6 for the 6 months. Same here, if you're working with t years subdivided into n periods, so each period is t divided by n, therefore the interest per period will be the initial interest rate that you have r divided by n. And this arrangement gives you the amount as p plus 1 times r divided by n raised to nt. Let me give another example on this. Is there any question first before that?
Yes, I do have a question.
Yes.
On the on the solutions, I wanted to ask, do we truncate the decimals or do we round off? Because I can see the answers, they were truncated, but for me it was rounding off and maybe getting a difference in the decimal places. I wanted to ask if you do round off, is it wrong?
That will depend on what the examiner is looking for, but I don't always give you answers to 2 decimal places for such kind of questions. Give you answers to 2 decimal places. And when I say 2 decimal places, you round off, don't truncate. Because if you truncate something like 15.87, if you truncate—
Actually, that one was 15.879.
Yeah, so that should have been 15.88.
Yes.
To truncate means to ignore. So don't truncate. You run off. Unless you're told otherwise. Always give your answer 2 decimal places. Round it to the nearest, round it to decimal places. Any other question? A sum of 1,000 shillings, 1,000 shillings is invested at 4% interest rate per annum. 1,000 is invested at 4% interest rate per annum. Find the amount of money after 3 years if the compounding is done. So number 1, let us have yearly. Number 2, semi-annually. Let's have quarterly, monthly, lastly, daily. So we want to see the different compounding periods and how they affect the amount of money that your money earns. The formula we're using is here. So we're using the formula A is P N raised to NT, where A is the amount of money at the end of the period, P is the principal amount invested, R is the interest rate, N is the number of periods, T is the number of years. So first is if the amount is compounded per annum, so if it's done yearly after every 12 months. The first one, A should be, the principal is just 1,000. That's the amount of money invested. Plus.
Sorry, sir. Could you please read what you actually wrote, please?
Here.
Yeah.
A sum of 1,000 is invested at 4% per annum. A sum of 1,000 is invested at 4% per annum. So 1,000 is the principal amount. 4% is the interest rate per annum. Find the amount of money after 3 years. So the time is 3 years. If the compounding is done yearly, or if you also write annually, it's the same. The compounding is done yearly, annually, semi-annually. So semi-annually means after every 6 months. So first 6 months is the first period, then the second 6 months, second period, third 6 months, all the way for 3 years. Then quarterly. So quarterly, I mean a quarter of a year. How many months are there in a quarter of a year?
3 months.
3 months. So this one you do computing after every 3 months. And then monthly. So the first month, January, calculate the interest, add. Use that to calculate the interest for February. Add that, use what you get to calculate the interest for March for all the 3 years. And then daily. So day 1 today, calculate the interest, add it to the amount, and then use that to calculate the interest for the next day. You do this for all the 3 years. Let us do this and see how much. Let us see how the period, how the number of periods affects the amount of money. Shall we proceed?
Yes, sir.
So if it is done yearly, it means it's just 1 year. So there's just one period in 1 year. Okay. So we will have 4%. 4% is the same as 4 divided by 100, which is 0.04. Okay. So I will have 0.04 divided by 1. The interest is 4% per annum. It's just 1 year. So N is 1. So put here, it's 1. Compute that, give me what you get. Semi-annually. Annually, the amount will be 1,000 multiplied by 1 plus 0.04 divided by. How many periods are there in 1 year? If you're doing it semi-annually. So 6 months and then 6 months. So each period is 6 months. How many periods will you have in 1 year?
2.
2 periods. So this divided by 2 raised to 3 times 2. What do we have here? What do you have for the first two? 3 we have now quarterly. So quarterly in a year, how many periods will you have? What's a quarter of a year?
4.
So a quarter of a year is 3 months. So that means you'll have 4 periods. So we'll have 1,000 multiplied by 1 plus 0.04 divided by 4. All of this raised to 3 times 4. Four is now doing it monthly. How many periods will you have in 1 year if you're doing it monthly? How many months are there in 1 year?
12.
Hello? How many months are there?
12.
In 1 year, there are 12 periods. So that means you will have 12 periods. So the meaning of that is that you invest the money in January, calculate the interest, add to the amount, add to the principal, sorry. Then what you get is what you use to calculate the interest for February. Do the same for February, get the interest, add to the amount. What you get here, use it to calculate the interest for March, all the way up to December. 1 year. So in 1 year, you will have a total of 12 periods. So that should be 3 times 12. What are you guys getting? Just put this in the calculator and press.
Excuse me,
What?
sir.
Yes, please, go ahead.
For quarterly, isn't it supposed to be over 3?
For quarterly. Yeah, that's a very nice question. Remember, we said n is the number of periods, okay? Are we agreeing? N is the number of periods.
Yes.
So quarterly, it means you're doing it after every quarter of an year. So a year has 12 months. A quarter of that will be 3. Is that okay? Hello? That will be 3. So it means you have an year has 12 months. Huh? So take 12 months. Each period is 3. 3, 3, 3, 3. So 3 plus 3 plus 3 plus 3 gives you 12. How many periods are there? So the first 3 months is 1 period. Are you together? Second 3 months is the second period. Third 3 months is the 4th period. And then lastly, 3 months gives you the 4th period. So quarterly, you will have 4 periods in 1 year, not 3 periods. You will have 3 periods doing the compounding after every 4 months. But if the compounding is after every 3 months, you will have 4 periods.
Okay, thank you.
Yes, you're welcome.
So I have a question.
Yes, go ahead.
So for monthly, what will be the value of n if you calculate January, February, March?
It's 12. N is 12. There are 12 months in 1 year. So that means there are 12 periods in 1 year. If you calculate the interest earned in January, and to the principal, do that for February, March, April, all the way to December. There are 12 months and you're compounding for every month. So it means you will have 12 periods. Is that okay?
So the answer will be the same throughout.
No, the answer is not going to be the same throughout. You guys should work out this and tell me what you're getting. The answer is not going to be the same throughout. Lastly, we have daily. Daily. So let's see. How many periods will you have?
365.
If you're doing it daily?
365.
That's if it's not a leap year. So let's assume we are not dealing with leap years. Okay? So that is 1 plus.
I have a question.
Yes, go ahead.
So if you're not told that it's a leap year, we just assume that it's 365.
Yes, yeah, just assume it's 365.
Okay.
Yeah, if you're not told. That's really not a big deal. My interest is that do you understand how many periods are there and how to do the compound? compounding. I'm not really interested in whether it's a leap year. So here, even if you use 366, I won't mind. I will just follow your working. What are these numbers?
Number 5, we have 11,274.89.
Number 5, huh?
Yes.
11,000.
11,000.
274.89.
89.
Yeah.
How about the
I'm
rest?
I'm getting a different answer as 1127.49, not 11,000. 1127.49. I don't know whether the rest are getting.
Oh yes, I used 10,000 instead of 1,000.
Use 10,000. So it's 1140. 1127.
1127.49.
Okay. How about the others? These other ones?
The first one is 1124.86.
1124.86. 86. How about the second one?
1126.16.
1126.
Yes, 0.16.
How about the third one?
1126.83.
And how about the fourth one?
1127.27.
What do you notice? It's the same amount of money invested at the same interest rate per annum, but we're doing the compounding differently. So in 1 year, so for the first one, we're doing the compounding per annum. Get the interest earned in 1 year, add it to the principal, use that as the principal for the next year, for the 3 years. The second one, we're doing the compounding after every 6 months. So in 2 years, 6 months periods will give you, in 3 years, sorry, in 3 years, 6 months period will give you 6 periods, 3 times 2, which is 6. So the first 6 months interest earned, add to the principal, use it for the next month, and do that for 3 years. That's why you get the 6 periods. So you notice that when you do the compounding per annum, the amount of money you get when you do the compounding semi-annually is more than when you do it per annum. So 1126 is more than 1124. This is not a coincidence. This is expected. If you do it quarterly, you get 1126.83, which is bigger than 1126.16. If you do it monthly, you get 1126.27, which is bigger than 1126.83. If you do it daily, you get 1127.49, which is bigger than 1127.27. So in general, amount earned increases with the number of compounding periods. With the number of compounding periods. The number of compounding periods. So what I mean is that in the first, I do the compounding once in a year. So there's only 1 period per year. In the second, I do the compounding after 6 months. So that gives me 2 periods in 1 year. And you see 1126 is bigger than 1124. So if you increase the number of periods from 1 to 2, you get more money, more income, more interest. If I do it quarterly, now instead of 2, I have 4 periods. I'll also get a bigger interest all the way up to per day. So someone will ask, what if I increase the number of compounding periods indefinitely? Let's say I want to calculate the interest maybe per second or per millisecond or per microsecond. After every second, I calculate the interest. Then I use that for the next second, all the way, or even in less than a second. Will the amount of money increase indefinitely? That's the question we would like to answer. Any guess? What happens if we increase the number of compounding periods indefinitely? Let's say you have infinite compounding periods where the time of investment is very, very small, maybe microseconds, milliseconds, or picoseconds, or smaller than that. Do you expect this amount to increase indefinitely, or will it stop after some time? Any guess from you? Going by this trend, do you expect this trend to go on indefinitely?
I think it will have to stop at some point because you can't add hours or minutes to, if you're calculating per minute or per second, you can't add more per day or per time. That's my opinion.
Yeah, I think you are right. Do you remember the definition of E that I gave today? Definition of E? The answer is in the definition of E. And the definition of an exponential function. We define E as the limit as n grows bigger and bigger of this expression 1 plus 1 over n raised to n. Now let us see. We know that the amount of money invested, the return is this r over n raised to nt, where n is the number of periods, t is time in years, r is the interest rate per annum. Now we are asking, what if we increase n indefinitely? What if we increase n? We increase n indefinitely. Indefinitely. Now to understand this, I want to do a change of variables. Let a new variable m be given by n divided by r. So that means r divided by n is 1 over m. I've introduced another variable which is directly proportional to n. So when I increase m, n also increases. Now I can write this amount by this change of variables. So I'm moving away from m to n. I can write a as p into 1 plus. So when m is n over r, it means r over n is 1 over m. So this r over n becomes 1 over m. 1 over m. All of this raised to nt. So what is n? From here, or even from here, we can write n as mr. Multiply both sides by r. So where there is n here, I put mr. mrt. So this is p into 1 plus 1 over m raised to m. I'm applying the law of exponents rt. So the law applied here is that a raised to m raised to n is the same as a raised to the product of these exponents. Okay? Then as I increase the compounding period, as I increase n indefinitely, m also increases indefinitely. But from this definition, when n increases indefinitely, this number approaches Euler number, E. So when n increases indefinitely, when n increases indefinitely, we have the amount of money being given by P times exponent of RT. So this guy will become E. It's the definition of E. So as you increase n indefinitely, this expression 1 plus 1 over m raised to m becomes E. So we'll have E raised to T. This formula gives you the amount of money compounded continuously. Compounded continuously. So this is when you are compounding for every moment, less than a second, less than microseconds or picoseconds. So the amount of money will not increase indefinitely. It will have a limiting value given by P exponent R of T. As an example, what we had before, so that was up to question 5. So question 6 should be if it is compounded continuously. So the question was 1,000 invested at 4% per annum for 3 years. What is the amount of money? Find the amount of money. The amount of money if it is compounded continuously. So we have done 5 cases: daily, annually, semi-annually, quarterly, monthly. Now if it is compounded continuously, we use this formula. A is P exponent R to the T, where the E comes from the definition of E itself, which is where this value approaches as M grows bigger and bigger. So here, the amount will be P exponent RT. We know P is 1,000. We know R is 4%. We know T is 3 years. So after 3 years of continuous compounding, the amount of money will be 1,000 times the exponent of 4 divided by 100 times 3, which is same as 1,000 exponent 0.04 multiplied by 3.
Do you mind writing in bigger numbers? Oh.
Here?
Yes.
Okay. I'll do that, no problem. So we want to calculate the amount of money compounded continuously for 3 years. So in the formula, P is exponent, A is P exponent RT. We know from the problem that P is 1,000, R is 0.04, it's 4%. T is 3 years. So the amount will be 1,000 times the exponent of 0.04, all of this multiplied by 3, which should give you 1,000 times the exponent of 0.12. Work out that.
1127.50.
1120?
7.50.
0.50. So as you can see, this amount will not increase indefinitely as we increase the number of compounding periods. It has a limiting value. We will get that from the definition of E. So those are some of the definitions of some of the applications of this exponential function. Any question? Any question? Any question? We will look at logarithmic functions in the next class because we really running out of time. Any question? So today we have learned 2 things. Number 1, rational functions. It's just a quotient of 2 polynomials. Okay? Quotient of 2 polynomials, a rational function. Then we have looked at exponential functions at large. So, and we have said that any positive real number different from 1 can be a base for the exponential function. But the most important base that we use, mostly called the natural base, is E, which is Euler number, and the definition is the limit of this expression as M grows bigger and bigger indefinitely. And we have seen an application of this exponential function in population modeling, also another application in finance or investment. Any question on what you have learned today? Rational functions and exponential functions. Question. So in the next class, we will look at logarithmic functions, which are simply inverses of exponential functions. And then we will see some basic graphs of these functions. How do you draw the graph of a rational function? How do you draw the graph of a logarithmic function? How does the graph of an exponential function look like? What are some of the information that you can extract from a graph of an exponential function, rational function, and logarithmic function, etc.